Hello everyone. My name is Alexandru Militaru, and this is my very first talk. I'm very happy to be here. This presentation is mainly based on the work that I'm doing from my bachelor thesis, where I am using the deprogramming language to strengthen the security of the Linux kernel modules. This talk would not have been possible without the great support that I've received from my scientific advisors, Edward and Răzvan, and I want to thank them. D is advertised as a safe and fast systems programming language. We know it's easy to write an operating system in D, and many projects have proven so. We have PowerNex, XOMB, and Trinix. However, we don't know how hard or easy it would be to use D code into the Linux kernel. Why would we do that? Because, believe it or not, the kernel is still struggling with many buffer overflows and other ugly bugs caused by faulty pointer manipulation. Many of these bugs could be avoided if the kernel would be written in a language with array bounds checking and other safety features. In this case, D can be of great use, at least theoretically speaking. To find out how it is really like in practice, we decided to introduce D code in the existing C code base of the Linux kernel. But before doing that, we wanted to be sure that's really possible to use D code in a kernel module. So we tested with a dummy one. Here's how our workspace looked like, and this is our dummy module. It has just an init function where a function implemented in D is called, this one from here. To link these two files together in a greater object, we had to write a kbuild file where we instructed the kernel to place these two files together in a greater object. As you can see, the D object has a special extension, namely oshipped. By using this extension, we are telling the kernel build system that this object, it's already compiled, and it doesn't have to compile it anymore. It has only to link it with the others. So we had to precompile our D object, and we used DMD along with the -betterC flag because we wanted to get rid of the D runtime because we can't use it in the Linux kernel. After that, we inserted the module and everything was fine. Then we thought about adding a parameter to our module since almost every function in a kernel module has at least one parameter. So we added one parameter in C and then in that function in D. We recompiled, and when we inserted our module, this wasn't working anymore because of an unknown symbol. This symbol was the global offset table. We thought about trying to recompile with LDC and see if this behavior gets replicated. As you can see, no global offset table, and it worked just fine. We didn't discover why the DMD compiler was inserting this symbol, so in the interest of progress, we decided to move to LDC. And so everything you will see from now on, it's compiled with LDC. Having the proof of concept done with the dummy module, we wanted to introduce D code in a really hot part of the Linux kernel. But the kernel, it's a huge beast, and there are many parts worth strengthening in it. However, there's no place like drivers. A research published at NDSS 2013 measured different parts of the Linux kernel and discovered that the drivers represent the most significant part in lines of code of the kernel attack surface. Considering this, we thought that porting a driver is the best place to start. So we began to seek a suitable driver. In our search, we followed three criteria. First, the driver had to be relevant for the kernel community. The second was the driver had to be easy to test and benchmark. And the last one, the driver had to be of medium size in lines of code. Having these three criteria in mind, we chose VirtIO NetC, VirtIO's Nurture driver. The VirtIO's framework is widely used in virtualization, and VirtIO NetC, it's one of the most complex devices supported so far by this framework. It has 3.3 lines of code, K lines of code, and being a network driver, it's easy to test and benchmark. Having the driver chosen, we wanted to venture to the process of porting, but before doing that, we needed a plan. First, we need to port the data structures, and then to port the functions, the driver's actual code. Having the driver ported, we could make the first set of benchmarks. The following step was to deify the code to add the D features in the drivers. And the last step was to assess how the features affect the driver's behavior. So the first step was to port the data structures. We needed the data structures because the decompiler had to know the structs layout in memory to be able to use them. Some structs were defined right inside our driver, but the largest part of them came from the header. As Attila said, the level of branching in the header files, it's huge. And there were many structs to port, and we tried to avoid this step by using DPP. However, we encountered some problems, and we were not able to use it. And in the interest of progress, we decided to port the struct by hand. We thought that porting structs by hand won't be that hard, but 1 month later, we were still porting structs. This for sure is because of the high level of indirection and branching in the header files, but also because of some problems that we encountered. One of them was the empty struct. In C, this struct is an incomplete type, and its behavior is undefined in modern C specification. However, GCC permits this kind of struct, and its size is 0. In D, the size of this struct is 1, and this is great because it's part of the language specification. However, when interfacing with C, this is problematic. Consider the following struct. If struct empty, it's a really empty struct, then the D version and the C version of bigger struct will have different sizes and layouts in memory. So you have to be very careful when you have this kind of struct and you are trying to interface with C. Another problem that we had was when we tried to use bit fields in D code. As you know, bit fields are not, D doesn't have bit fields. But we could avoid that using the bit field implementation from the standard library. Another problem that we had was the fact that we can't introduce a version inside that bit field instantiation. But we also managed to avoid that by using string mixin. That evolve version template, it's returning that string if config something is defined, else it returns the empty string. So we replicated this behavior from C. After we ported the structs, we began to port the function. But after we ported the first function, our kernel was crashing. After some hours of debugging, we discovered that the parameters that were used inside the functions were completely different than the one that were passed when the functions were called. This was because of the calling convention. The 32-bit ABI calling convention is that if you have a function foo with A, B, C, then the caller will place the parameters on the stack in the following order. And the callee will be able to access them as in the following figure. However, the parameter mismatch was caused by the fact that modern 32-bit Linux kernels are passing the first 3 parameters in registers as an optimization. We've learned that the 32-bit kernels are compiled by default with the mreg parm equal 3 GCC flag that tells the kernel to pass the first 3 parameters in registers, and if they are more, to place them on the stack. How we solve this problem? We compile the kernel for 64 bits. On 64 bits, the kernel is using the standard System 5 calling convention. That means the first 6 parameters are placed in registers, and if they are more, they are placed on the stack. On 64 bits, LDC is doing the same. Another problem that we had was after we ported the first static array. After we've done that, we could no longer insert our module because of an unknown symbol. This symbol is the name of the assert fail function from the C runtime library. We have learned that since we used the -better C flag for compilation, the asserts are altered to call the asserts from the C runtime library instead of the D runtime library ones. And this is great, but the kernel has no runtime library to use, and the assert symbol will remain undefined. Our workaround was to define our own assert function with a minimal implementation, a call to the kernel's panic function, and a warning message. We prefer this instead of a security breach caused by an undetected buffer overflow. Another problem that we had was when we ported when we wanted to use function pointers in D. We had an array of function pointers that we iterated over it and initialized each pointer with the address of a function. After we've done that, we could no longer insert our module because it had an invalid format. And the unknown relocation was issued. When we looked at the relocation section of that function, we discovered that when the addresses of those 2 functions were taken, this type of relocation was issued, GOTPCREL. This type of relocation is using the global offset table. Now let's look a bit at the function that the kernel uses to resolve relocations. It's not very hard to understand what's happening here. This function has a switch that handles many types of relocation. However, GOTPCRL is not one of them. And this switch will end on the default case, and the unknown relocation error will be generated. So we had to do something to avoid this. Our solution was to create 2 wrapper functions in D that just return the addresses we needed. And we used them in D like that. And now we had 2 different types of relocation, PLT32, one that the kernel knows how to handle. This type of relocation hit us again when we ported the first global array. We had this array of structs in C that we ported in D like this. There were many functions that were accessing this array, and one of them looked like this. We inspected the relocation section of this function and discovered that the array access generated once again this type of relocation, and we already knew that the kernel it's not able to handle this type. So once again we had to do something to avoid it, and here the problem was that this array should have been placed in the raw data section, but it is not, and we don't know why. But we've tried to get it there by using first immutable, and the problem persists. Then we tried to use enum for that array, and a type info error was generated. What really solved the problem was to make the array immutable enum, and so a new type of relocation was generated, and the array was placed in the raw data section. Another thing that solved the problem was to make the array enum and specify the size, and this type of relocation was issued again, and the array was placed once again in the raw data section. After we ported the structures and the functions, we had an up and running dwritten module. So we could make the first set of benchmark. As a reminder, our module it's a network driver. So to benchmark it, we created a virtual machine using QEMU and measured its network performance using iPerf3. Basically, we created 3 client-server connections, host to guest, guest to host, and guest to guest, and we sent packets for a fixed period of time to see what bandwidth was achieved. Then we've done the same for the C version of the driver and compared the results. Here they are. As you can see, the D and the C version are almost the same. The dwritten one has a small decrease in performance between 1 and 4%, but considering the fact that there are still some bindings, that means D functions that only call C functions that could not be ported, this difference is explicable and also fairly insignificant. After we've done the first benchmark, we began to add features in the driver's code. There are some things to do, but we've done some of the most important ones. One of them was to add bounce checking, and this is a big plus for the driver security. Let's have a look at this function. Here, an index it's magically computed, and then this array is accessed. So simple and remarkably unsafe. To strengthen the security of this kernel module, we had to add bounce checking everywhere this kind of access was done. But how do you get bounce checking when you have the parameter of the function a pointer and this same queue that is accessed there also a pointer? We don't have any information about length. After we analyzed our driver, we discovered that there's a function where every struct of this type varnet info it's allocated along with its queues. So here is the length information that we needed. To use this information, we created the wrapper struct that had 2 slices, one for the send queues and one for the receive queues, a pointer to the original varnet info struct, and the 0 length array that we used to for container of. Then we've modified the function where those queues were allocated we declared a pointer of the type of our wrapper struct. We allocated memory for it. And then each slice got a chunk of that extra memory. And then we made the old queues point to the new ones from our wrapper struct, the ones that also have bounce checking. Now, let's see this wrapper struct in action. Remember this function? Now it's safe and also has bounce checking. Our change was simple but effective. Everywhere a queue was accessed through a VerNet info struct, we brought our wrapper struct using container auth, and then we modified the access to be done on our queues that also have bounce checking. Another thing that we've done was to use templates where C was using void pointers to achieve generics. We had this struct in C that's this is a representation of a device in the Vert.io framework. It has a void pointer that holds a reference to something. In our driver, this reference was always to a VerNet info struct. So everywhere a VerNet info struct was needed, it was extracted in the following way. And this works because in C, the void pointers are automatically converted to any other type of pointers. But this is very unsafe. You can be sure that this void pointer, it's really a pointer to the type you think it is. In D, this is done with a cast. Also, if you don't make a cast, it won't work. So why don't use a template instead of this void pointer and also have the type system on our side? What you've done was to template this struct, and then we made an alias, and then we measured how many casts of this type were done, 13. After we've used the template, 0 casts, all gone, and the driver is also safe. After we added some features, we also made the benchmark. The second one, as you can see, the D and the C version are pretty much the same. There's a very small decrease in performance between 1 and 4%. As future work, it would be nice to use link time optimization because there are some functions that are still in C and the compiler can't inline them. It also be nice if we would write down the issues that we've encountered and hand them to the D community. Maybe we can work together to solve these problems. And another great thing would be to make DPP work, because this would save a lot of tiresome work. As conclusion, D can keep up with C in the Linux kernel, but being through all this process and seeing all the issues, we think it's better to write a driver from the scratch in D. But our project also proved that it's possible to port one incrementally. And a compiler switch for the issues encountered for relocation in special would be very nice. Thank you for your attention.
Alrighty, and again, we have time for one question, and it's from Walter.
I suspect that the slowdown is caused by, instead of calling functions directly, you're calling through function pointers. That would incur a little bit of slowdown, and it may just, completely explain why you're seeing that slight decrease in performance. The second thing is all the issues you had in there are solvable. So I'm going to be a broken record and say I need a Bugzilla for each of those issues, and then we can attack them one by one and get them resolved.
Cool.
All right, thank you, and thank you.